In this final video, I want to talk a little bit about what's called slice timing correction, which essentially is the same issue as realignment, but rather than realigning in space, we're going to be realigning in time. So in normal scenarios, and we talked about this a little bit again when we talked about sampling bias, we don't acquire the whole brain in one shot. We acquire it in sets of 2D planes. And normally we do it in sort of either a descending order. We do a plane here and then below it and then below it further, and then until we repeat. Or we do it in ascending where we sort of go up. It's also possible to do it in a slightly more complicated method called interleaved, which we'll talk about in a minute. But it does mean that it takes a certain amount of time to go from one point in the brain up through the rest of the brain and then back to that point again. And that's the repetition time, right? And that means that we have this biased sampling of the hemodynamic response function because we're measuring it literally at different points in time. So if, for instance, you have, like down in Buckney, what we would normally use is about a 3-second repetition time, and we would measure 36 axial slices, which means that on average, each slice takes 85 milliseconds, right? Under those circumstances, the first one's at 0, the next one's at 85, the one after that's at 170 milliseconds, etc., as you go all the way through the head. And that means that we're not getting, even if all of the underlying data look exactly the same, we're not measuring that the same way. And I'll show you an example of this. The question then is, can we correct for this sampling bias by interpolating the time series and trying to take into account when we acquire it in the volume of the head? So, as I said, this is a very, very simple schematic of an ascending sequence. This isn't realistic. I just couldn't put 36 slices on and make it visible in the image, so I've just put 8 slices on, used a 2-second TR, which means that each slice takes 250 milliseconds. That's not what happens in a scanner, but just to illustrate the process, you can see that by the time you collect, if you collect something that's started at time 0, if you're in the middle of the brain, you're not even getting to it to measure it until it's already a second in. And as we talked about previously, that can bias your sampling of the hemodynamic response function. So this is an example, right? So here we have slices, only labeled 1 to 5. And what's happening is at the time that's labeled 5 here in the plot, where's my cursor? I've lost my cursor. I'll video edit something. But at the 5th TR, you can see that a hemodynamic response, a bold increase, has initiated in all 5 slices, right? They're all going up and down exactly the same. However, the data that we measure from those 5 slices isn't the same, and that's what's shown in the bottom slices. So in slice 1, there's been very little time for the hemodynamic response to actually start to rise, so we have a small measure. By the time you get to slice 5, you've almost gotten the full amplitude of the hemodynamic response. And the important thing to see here is that in one case, you're getting a good sampling. In one case, you're getting a sort of an awful sampling. And that's still within a single volume, a single TR, right? Even though the underlying response that we're trying to measure is exactly the same. They don't look the same in the measure that we've taken. And that's because of this sampling of the hemodynamic response function and the fact that it plays out over time rather than being an instantaneous measure. So just to sort of illustrate this, again, if we just take something from the bottom slice here, and we sample it at 0, 3, 6, etc. This is the hemodynamic response that we estimate. In contrast, if we use something higher up in the image and we sample it at, like 2, 5, 8, etc., then you get a different estimate of the hemodynamic response. They're not wildly different, but given that the effect sizes that we're measuring are small to begin with, anything that biases you for or against measuring it accurately is something that we need to avoid. And that's the problem with slice timing, and that's what people are talking about in terms of using a slice timing correction. Can we come up with a reference volume that we're going to say is the neutral point and adjust everything so that it acts like we acquired it all at that same point in time? And that formulation hopefully sounds incredibly familiar to what I just said in previous videos, where we're going to create a reference volume image in space and use that to sort of estimate how much motion has happened, and then can we realign the data in order to minimize the effects of that motion. Well, that's the same problem that we're doing now in time rather than in space. We're going to take a reference slice, and we're going to say, well, that's our 0 point. Now everything is going to be relative to that 0 point. Can we adjust this through interpolating the data in order to make it so that it acts like we collected the data at this point in time? The other kind of acquisition, which is fairly common and is worth sort of mentioning, is there are interleaved acquisitions. So rather than going sort of bottom to top or top to bottom, you can do something fancier. And I'm just sort of illustrating that here, where you skip a slice. So the first slice is, say, at the bottom. You then skip the next slice, and the second slice is the third slice up, etc. And then you go back and fill in with the missing slices. So now, rather than take one slice and the next slice is in space is also the next slice in time, you're breaking up that relationship between space and time. And this is in order to try to de-bias the sampling of the hemodynamic response function. And that, you can see that illustrated in this figure. There are different consequences to slice timing correction depending on whether it's an ascending or descending sequence versus an interleaved sequence. But there are a couple things that they have in common. The first is that it does require a short TR to be a sensible thing. The longer the repetition time, the more space you have to get your interpolation wrong. So short TRs, 3 seconds or less, are best if you're going to do slice timing correction. If you do an interleaved acquisition, then you normally do the slice timing correction before you do spatial realignment. In contrast, if it's a sequential acquisition, up or down, then you normally do realignment first and then you do slice timing corrections after it. I don't really want to go into the whys and what for of that, because the actual main point that I want you to take out of this is, unlike spatial realignment, I don't think you should actually use slice time corrections. And the reason for that is because there's a difference between what you need to do in order to make your statistics appropriate. So that is, make sure that the data are lined up so you're analyzing the same source of bold signal throughout the whole time series, versus dealing with this sort of temporal sampling problem that can be handled while you do your statistical modeling. So that is to say, there are two ways of dealing with these sources of variance. They are remove them through some sort of image preprocessing, or model them when you're doing your statistics. So that is to say, use the right statistics to match your data. Don't change your data. For our purposes, we need to change the data to deal with the sort of issue of motion realignment, spatial head movement. However, we don't need to change the data to deal with the issue of temporal sampling. That we can deal with by introducing something known as a temporal derivative, which we'll talk about when we talk about first level analyses. So to my mind, anytime you can deal with sources of variance using statistical modeling rather than changing the data themselves, that's the optimum approach. And that seems to be the sort of industry standard. The vast majority of people don't use slice timing correction. They simply deal with it during their using the general linear model by adding temporal derivatives. And we'll talk about the details of how and why and what for that in a few weeks. Okay, so across the videos in this week, the main take-home messages are: every time you start up a scanner, you get these T1 longitudinal effects at the beginning of each run. And as a result, you're going to need to delete a certain number of volumes to simply just get rid of those extra bright volumes. Critically, you don't want your experimental paradigm going during that time because you're throwing out those data as well. Or you want to use your experiment to get them practicing, but you're planning to throw those data out. You always need to do some kind of realignment to deal with the fact that people's heads move during scanning. The process is fairly straightforward, involving estimating the motion parameters and then interpolating the data to try to do this realignment process. But what it doesn't do is correct for motion. It makes a step in that direction, and it deals with some of the first order linear effects, But there are all sorts of other effects that are still there, including partial volume effects, edge effects, field of view effects, within volume motion effects, and distortions that are related to the fact that people have moved their head within a magnetic field. So that's why I avoid the term motion correction. I will encourage you strongly to not refer to motion correction. There's a reason SPM calls it realignment instead of motion correction, and that is because it is realigning the data. It is not correcting for motion. And then finally, slice timing correction is essentially the same as head movement correction or realignment, but rather than in space, it's done in time. And it's to deal with the fact that we're not acquiring the hemodynamic response function at the same point in time throughout the whole head. Now, I would encourage you not to use slice timing correction when you do your data. It shouldn't be part of your pre-processing steps. Instead, it should be handled correctly when you do your modeling, because it's something that we can take into account very easily and naturally within the framework that we're going to use statistically. And it's always better to make your stats match your data rather than to change your data to match the particular stats you have available. And as always, some suggested readings. This week, I want to suggest a chapter in the Poldrack, Mumford, and Nichols book on pre-processing MRI data. There's some more detail in there that's very useful, and I recommend that you take the time to go through it. I know that some people in the class have much more of a mathematical background than others, but for everyone, it's actually useful to make an effort to try to understand these processes, even if it's just conceptually. But if you understand it at a deeper level than that and can actually, for instance, do the math yourselves, then you will be less likely to make errors in terms of using it. Thank you very much.